This next set of movies is on a topic that you touch on ever so slightly at A level in a way that I find extremely unsatisfying because it stops before you get to the fun part. But then I've also been told that it's considered that the fun part is too difficult for you. And so it's not done. Well, I thoroughly reject that concept because it's such fun that I know you can't fail to enjoy it and understand it. And that's to have a closer look at the bonding in particularly in this case octahedral coordination compounds, and then to see how that affects in particular the color that we see for transition metal compounds. You're told at A level that they're colored. You're told one sentence about why that is, and then it's left alone. So let's go more deeply into that, shall we? Now, before we get there, we have to remember that in an atom, you have 5 degenerate d orbitals, which I'm going to draw down the bottom there as 5 straight lines. Now, those d orbitals have some fun little shapes. Here's the shape of one. This is an orbital that you can think of as being a p orbital with a belt, except that a p orbital, of course, has different shadings, a plus lobe and a minus lobe. In this particular orbital here, both of the lobes are the same sign, and it's the belt that is the opposite sign. Now you can see that the bulk of this orbital lies along the z-axis. So this is called the dz squared orbital. Now the second orbital is this one here. It lies on the x and the y-axes, so it's called the dx squared minus y squared. The red lobes I'm drawing along the x, and those would be the positive lobes if we were worried about the fact that these are waves, and then the blue shaded ones I've got along the y-axis, and it would be the negative lobes. Not that that matters much to us right now. Essentially though, we have two orbitals that we're going to say lie along the axes. So we got the dz squared lies predominantly in the z-axis, the dx squared minus y squared lies predominantly along the x and the y-axes. So that's two of the orbitals that in a minute you're going to see correspond to these black lines down here. Now the other three orbitals are ones that are exactly the same shape, and it's just their orientation that differs, and trying to draw this in 3 dimensions was a challenge. But anyway, here's the first one, and this is supposed to lie in the xy plane, okay, but it lies so that it's in between the axes. So you can see, I hope, this red lobe here is pointing out right between the x and the y-axis. This blue lobe here is pointing right at you between the y and the minus x-axis. This one here is between the minus x and the minus y, and then this one here is pointing straight between the x and the minus y axis. So that sort of shape, it's you could call it a 4-leaf clover shape. Essentially looks almost like this, except while this lies along the axes, this one is lying in between the axes. And it has two equivalent friends. If this is the one that was lying in the xy plane between the x and the y axes, this is the one I've tried to draw in the xz plane. So you can see this little red lobe here pointing out in the plane of x and z, but in between the axes there. This one here is supposed to be the YZ plane. So you can see maybe this lobe here pointing directly between the Y and the minus Z axis. So these are called, not surprisingly, DXY, DYZ and DXY, DXZ and DYZ based on which axes they lie in between. And I'm going to group these three together to say they are between the axes. Okay. Now, what was known, and we're going to explain or try to explain some theories as to why this is that the orbitals split, right, when the metal atom forms complexes. And in particular, for an octahedral complex, they split so that you have 3 orbitals that go in a lower energy and 2 orbitals that go in a higher energy. The 3 orbitals that are in a lower energy are the ones that are between the axes, so the dxy, the dxz and the dyz, that's these 3. And the ones that go increased in energy are the ones that are along the axes, the dz squared and the dx squared minus y squared. And so there is a splitting between what were degenerate equal energy, 5 equal energy orbitals, to a set of 3 and a set of 2 that now have an energy difference between them. And of course, that last bit is what you were told at A level. You have the orbitals split, the 5 equal energy d orbitals split into 2 sets, lower energy, upper energy, with an energy gap between them. So that's splitting here, right? This change between 5 equal energy orbitals to 3 and 2. That energy split there leads to some fun electron configuration issues. Start off with D3, right? So this would be a metal or a metal cation that has 3 d electrons. Well, you can see that when you put those 3 electrons into these d orbitals, it's easy. 1, 2, 3, going into the 3 lower energy ones. Now then when you get to D4, so we've got to stick another electron into here. Where does it go? Well, you would say, of course, well, it will go in here because that's the lower energy one. But that's not always the case because, of course, when it goes into here, now you've got a little bit of repulsion going on with the electron that's already in there. Maybe it would go there. And whether it goes here to pair up or up here to go on its own depends upon how the energy that is bad associated with the repulsion compares to the energy difference between this and this level. Okay, so let's consider first of all where this is a really small energy difference. In other words, the splitting hasn't been too much. Well, in that case, that 4th electron is going to pop in there, no problem, because this small energy difference is not as bad as the energy would be if it's pairing up with an electron that's already there. In other words, this energy difference, this energy gap is less than the repulsion energy. But imagine that this one is a really high energy difference. Well, in that case, there's a huge extra energy needed for the electron to go there. It will go in here and live with the repulsion. Okay, now these two scenarios are called high spin versus low spin. High spin is where you got one, in this case 1, 2, 3, 4 electrons all spinning together in the parallel direction. And you get that high spin when that 4th electron can go into the higher energy orbitals because there's a small energy gap. This here is called the low spin because 2 of the electrons are cancelling each other out spin-wise. One spinning one way, one spinning the other way, they cancel out. You get low spin when it's preferable for an electron to put up with the repulsion and cancel out the spin than it would be to go in the higher energy orbitals. Okay, so D3, no problem. D4, you have high spin and low spin depending upon in the complex whether this separation, this energy separation when the complex was formed is a small difference or a large difference. Now you can continue to have high or low spin possibilities for D5, D6 and D7. In fact, let's count some of those up, shall we? There's D4. Put in a 5th one when this is small and you get there D5, so that's high spin D5, high spin D6, high spin D7, and then high spin D8. What you'll see in a minute is there's no difference between high spin and low spin. Remember, the high spin went 1, 2, 3, 4, 5, 6, 7, 8. Now, if we go to the low spin situation, so we go on 1, 2, 3, 4, where would the 5th one go? Well, the 5th one, again, this is a huge energy gap here. So the 5th one will go and pair up. So that's D5. Low spin D5, they're all in these lower group. High spin D5 was 1, 2, 3, 4, 5. 6th one for the low spin goes in there. So low spin D6, all of them are in the lower group. High spin D6 would have been 1, 2, 3, 4, 5, 6. So in other words, 4 in the lower group, 2 in the upper group. Low spin D7. Now finally, we filled these low energy ones, so we got to put one in this higher energy, even though there's a really big gap. So this is low spin D7. Again, if you'd remember, high spin D7 has got 2 here, 2 here, 1 there, 1 there, 1 there. So 5 and 2 as opposed to 6 and 1. But now when we get to the low spin D8, got to put the electron there. You can see the high spin and the low spin for D8 are exactly the same. So we don't worry about high spin for D8, D9, D10. So D1, D2, D3, no differences, no special considerations when you've got an octahedral compound. D4, D5, D6 and D7 you have to worry about low spin or high spin. D8, D9, D10, again just one possibility.